So far we've talked about how things move in space and why they move the way they do, and then we've learned about light and how we can study light and learn a lot about what produced the light when we study its spectra. And so now we're going to apply all of the knowledge to studying the solar system. So this will just be a brief introduction to the solar system, and then we'll go in more specifics about each planet over the next couple weeks. So our goal for today is learning what the solar system looks like, and then at the end we'll talk about the theory we have for how the solar system formed. So if we look at the orbits and the rotations of all of the planets in the solar system, all of the orbits all go in the same direction. So if you're looking kind of from a top-down view, all of the planets orbit the sun counterclockwise. And then all of their rotations, except for one, are also counterclockwise. So all of the planets spin on their axis in a counterclockwise way when looking from above, and they all orbit the sun counterclockwise. The sun also spins on its axis, and it spins counterclockwise as well. The exception to that rule is Venus. So Venus actually rotates very slowly in a clockwise direction so it's the opposite of all the other planets. So when we come up with our theory for how the solar system formed, we're going to have to explain why all of the planets orbit and rotate the way they do, but Venus is different. The planets fall into two main categories. There are the terrestrial planets, which are small rocky planets, and then there's the Jovian planets, which are the large gas giants. There are also smaller objects that aren't planets that populate different areas in the solar system. So this red ring is the asteroid belt that's in between the orbits of Mars and Jupiter. Then beyond the planets of the solar system, there's the Kuiper belt, which is the belt that's further out from the sun, so it's farther than Neptune's orbit. And then this cloud of stuff even farther out than that is called the Oort cloud. So in the Kuiper belt and the Oort cloud, that's where you'll find comets, so those are icy things. The asteroid belt is mainly rocky things. So like I said, there's some exceptions to the rules that we talked about earlier. So Uranus its axis is tilted almost 90 degrees to all of the other planets. So if you want to think of the Earth does have a tilt to its axis of rotation, which was the 23 degrees. That's responsible for the Earth having seasons. Uranus's axial tilt is even more extreme than that, almost 90 degrees. And then compared to all of the other moons in the solar system, the Earth's moon is actually relatively large to the size of the planet that it's orbiting. So there are moons in the solar system that are larger than our moon, but they are much smaller than the planet they're orbiting. So again, when we come up with our theory for how the solar system formed, we need to explain these exceptions to the rules. Okay, so if we want to get a sense of the scale of the universe, we can shrink everything down to about the size of the area of Charleston and Mattoon. So if we put the sun right at the corner of 4th Street and 16, so just right outside of this building, then you get Mercury, Venus, Earth, and Mars all before you leave Charleston. And then as you're heading out towards Mattoon, you'll get Jupiter and Saturn before you hit the airport, Uranus a little bit past the airport, Neptune all the way in Mattoon, and then Pluto past Mattoon even farther out. And if I were to actually have this drawn to scale, the planets themselves, you wouldn't be able to see the dots on the map. So planets are very small compared to the distances between them. So if we start from the center of our solar system and work out, from there we'll start at the sun. So the sun is 99.8% of the mass of the solar system. So really, if you want to study the solar system, you would only study the sun. That's most of the stuff that makes up the solar system. It's mostly made out of hydrogen and helium gas, and further in the interior of the star is plasma. It converts 4 million tons of mass into energy every second, and when we learn about stars in a few weeks, we'll talk about the nuclear reactions that are happening in the core of the sun. And so, to give you a sense of scale, this is the size of the Earth next to the sun. So you can fit 1 million Earths inside of the sun, basically. The next object out from the sun is Mercury. So this is the first planet out from the sun. It's mostly made out of metal and rock. It has a large iron core. The surface of it is not very interesting, except for the fact that it has craters and some cliffs. The side that faces the sun is very hot, 425 degrees Celsius, and then the side that doesn't face the sun is very cold, minus 170 degrees Celsius. So large temperature differential between the side facing the sun and the side facing away from the sun. Venus is the next planet out from the sun. It's almost the same size as the Earth. It has a very thick atmosphere that's a result of a runaway greenhouse effect, and so it's hard to study the surface of Venus because it's hidden by clouds, but we have landed probes on the surface of Venus that we'll see later in the semester, and it's even hotter than Mercury is because it has an atmosphere to trap all of the heat from the sun that hits the planet. So even though Venus is the second farthest from the sun, it's actually the hottest planet. Then the third planet out from the sun is the Earth, so that's where we live. We have life, we have liquid water on the surface, and we have a surprisingly large moon compared to the size of our planet. So we didn't talk about moons for Mercury and Venus because they don't have moons. Mars is the fourth planet out from the sun and the last terrestrial planet. So it kind of has similar features to the Earth. It has volcanoes, canyons, polar caps, but it has a very thin atmosphere, so if A, it's cold, and B, there's no oxygen to breathe. So if humans ever do make it there, we're not going to be able to walk around without a spacesuit. We think that water flowed on the surface in the past on Mars. So we know, or we think that you need water to have life, and so if there was water on the surface of Mars, could there have been life? There's been recent discoveries that are leading people to believe that there was life on Mars, and we'll talk about that when we talk about Mars in a little bit. So the 4 terrestrial planets are closest to the sun, and then the next planet out from the sun is Jupiter, which is a gas giant. It's much farther from the sun than any of the terrestrial planets. It's mostly made out of hydrogen and helium, so all of the inner planets were rocky, and now the gas planets are mostly gas. It's 300 times more massive than the Earth, and it has many moons. It actually does have rings that you can see, especially if you look in the infrared. So Saturn is not the only planet that has rings. And the moons of Jupiter are just as interesting, if not more interesting, than some of the planets in the solar system. So this is an artist's rendition, so you can kind of see the ring around Jupiter, and this is looking at the planet, or the surface of the moon Io, with the planet Jupiter in the background. So the 4 Galilean moons, so these were the moons that Galileo could see through his telescope and that he used to help disprove the geocentric model. And so the closest moon to Jupiter is Io. It has active volcanoes on the surface. It's the most volcanically active object in the solar system. Then Europa is the next one out from there. We think it has a solid surface of ice, but we think there might be a subsurface ocean underneath of that ice. And so this is one of the places in the solar system that we want to send a probe to look for life. Ganymede is the largest moon in the solar system. And then the next moon out from there is Callisto, which is a large ball of ice that has lots of craters on it. The next planet out from the sun is a lot of people's favorite. So this is Saturn. Of course, the most prominent feature are the large rings. And it's also a gas giant like Jupiter, so made out of hydrogen and mostly helium, or mostly hydrogen and some helium. And it also has a lot of moons, and the most remarkable moon is Titan, and Titan has a very thick atmosphere. So that's another place where we would like to look for life, because while it doesn't have liquid water on the surface, we think it might have liquid methane, and having a thick atmosphere is important for protecting life from harmful cosmic rays and radiation from space. So the rings of Saturn are not solid objects that are rotating around the planet. So they're really small chunks of rock and ice that are all orbiting the planet in a disk shape. So you can think of the rings of Saturn are just millions of tiny moons that are orbiting Saturn, and rings are not a permanent feature of a planetary system. So we're just kind of lucky that we happen to live in a time where Saturn has these nice rings for us to look at. The next planet out from Saturn is Uranus. It's smaller than Jupiter and Saturn, but it's still much bigger than the Earth. And it also has hydrogen and helium gas, but it also now has some hydrogen compounds, so water, ammonia, and methane. Like we said before, it has an extreme axial tilt, so if you imagine a normal planet should have 0 degrees axial tilt, the Earth has 23 degrees, and Uranus almost has a 90-degree axial tilt. And it has lots of icy moons, and it does also have a ring system. And the last planet out from the sun is Neptune. It's similar to Uranus in that it has hydrogen, helium, and then hydrogen compounds making up its atmosphere and gas. And it has also a ring system and many moons, including Triton, which is another very large moon that humans are interested in sending probes to. Farther out from Neptune, there are other objects, but they are not classified as planets. So, for example, Pluto is a dwarf planet. This is an actual picture of Pluto and its moon, Charon. They're icy, so they're not like the gas giants that we just talked about, and they're not like the terrestrial planets that are made out of rock. So these are icy, and they're more similar to comets in their makeup than any of the planets. And if you compare the size of Pluto and Charon to each other, they're very close in size, and they behave as more like a binary system rather than a big central object and a smaller thing orbiting around it. So we'll talk about different kinds of binary orbits when we talk about stars later in the semester, and you'll see what kind of different orbits two objects can have that are orbiting each other. So then beyond Neptune and including Pluto are objects in the Kuiper Belt. So these are all of the comets that, and the range of orbits extends from 30 to 50 astronomical units. So remember, 1 astronomical unit is the distance from the sun to the Earth. So these are 30 to 50 times farther away from the sun than the Earth is. There's hundreds of thousands of comets that are more than 100 kilometers across, and some of these, the orbits of Kuiper Belt objects are not all circular like we have for the planets. Some of them are highly elliptical, and so they do cross the orbits of some planets. So we'll talk about a comet that impacted on the surface of Jupiter later on, and if you're worried about life on Earth, then you have to be wary of things that cross Earth's orbit, whether that's an asteroid or a comet from the Kuiper Belt. Then even further out from the Kuiper Belt, there's this cloud of comets around the solar system called the Oort cloud. This extends out to 50,000 astronomical units, so 50 times farther from the sun than the Earth is. And there's trillions of comets, and they're not all in a nice disk like the Kuiper Belt. They're in this spherical cloud, and they have random orbits and tilts and highly eccentrical orbits that are hard to track. So put the order of the terrestrial planets, put them in order, starting from closest to the sun and working your way out from there. Yeah, so the correct order: Mercury, Venus, Earth, Mars. And then we'll do the same thing for the gas giants. So put them in order, going from closest to the sun and working your way out. Yep, so Jupiter, Saturn, Uranus, Neptune. So we've kind of seen the order of the planets and some of the key features of each of those planets. And over the next couple weeks, we'll go into more detail about each of the individual planets, and we'll also learn about some of the moons as we work our way through the solar system. So now that we've kind of seen a broad overview of the solar system, we need to come up with a theory to explain how it formed. So we'll talk about those features that point towards a theory that we can come up with, and the theory that we've come up with is called the Nebular Theory. So what is the Nebular Theory? So the Nebular Theory is that our solar system, and as it turns out, all of the star systems in the galaxy and in the universe, all start from a giant cloud of interstellar gas. So from this giant cloud of gas, you'll get the gas cloud will collapse. At the center of the gas cloud will become very hot and a star will form. That star will do nuclear reactions and release light into the universe. And eventually the star will no longer be able to do its nuclear reactions, and it will explode in one of several different ways, and it will recycle that material back into the galaxy, and then the next generation of stars will be formed from the gas that was left over from the previous generation of stars. So the sun is what we call we think it's a third generation of stars. So there's already been two previous generations of stars that have formed, lived through their life cycles, died, and recycled their gas back into the universe. And so when we learn about stars and the conditions that were around at the very beginning of the universe, we'll see that all of the elements beyond helium had to be made either in the cores of stars doing nuclear fusion, or as a result of the stars exploding and creating even heavier elements. So, for example, humans are carbon-based life forms, so carbon was needed. You needed a star to make carbon and repopulate the galaxy with that carbon. The Earth is made of silicon, so the solid surface that we're standing on wouldn't exist if it wasn't for stars doing nuclear reactions and blowing up and sending that material back into space. We are stardust, basically. We see evidence of gas clouds in space in various stages of the process of forming solar systems, basically. So we see this happening in other places out in space, so we assume that this is the same process that led to the formation of our solar system. Obviously, we weren't around to witness the formation of our own solar system. That was billions of years ago. So this is a picture of the Orion Nebula, and you can see various regions, little clumps where there's either a star forming in the center of the clump or a star has already formed. And so these are kind of the baby pictures of solar systems forming. So the nebular theory is the theory for the formation of the solar system, and it says that in the Milky Way there was some giant cloud of gas that part of that gas cloud started to collapse. In the center of that collapsing gas cloud, the sun formed, and then all of the planets formed around the center of that collapsing gas cloud, and the solar system was formed. So we're going to use some of the physics terminology and mechanics that we learned over the last few lectures to explain how you go from a giant gas cloud to planets forming. So our theory needs to explain why all of the planets orbit the sun in the same direction and why they almost all rotate around their axes in the same direction. Why are there different types of planets? Why are there rocky planets and gas giants? Why are there asteroids and comets? And then those exceptions like Uranus having a high axial tilt and Venus rotating on its axis in the opposite way. Can we explain those things using our nebular theory? So the first physics term that we're going to invoke is conservation of angular momentum. So if you have this cloud of gas that starts in some kind of spherical shape, as it starts to collapse, it's going to become an even smaller shape. And so when we talked about angular momentum, if you had your ice skaters spinning with their arms out, and then they brought their arms in, they started to speed up. So the process of this gas cloud collapsing is going to make the particles start moving faster and heat up, and all the particles are going to start rotating in the same direction due to conservation of angular momentum. Then as the gas cloud starts to collapse in on itself, why does it form a disk? So you have collisions within the gas cloud. So basically all the particles are moving around and some of them are hitting each other. When two objects collide, we need to use conservation of momentum to describe that collision. And basically all the random orientations of momentum that something can have in a spherical gas cloud will all average out to the particles as they start to collapse. Instead of going from a spherical gas cloud to a smaller spherical gas cloud, they'll collapse into a disk shape due to conservation of momentum. And so we see these disks around other stars. So these are real pictures taken with various telescopes. So on the left is a picture in the visible wavelength range from the Very Large Telescope in Chile. And so they've put just something dark in front of the central star on their telescope so that it doesn't wash out the rest of the picture. And now that the bright star in the center is blocked out, you can see the gas cloud around that star. And you can even see, we think this little region here is a planet forming around this star from the gas that's left over from the nebula that the star is forming from. And then on the right is another visible picture. And then this inset is a radio image, again showing the disk that forms around a star as it's forming. As the gas cloud collapses, we have a lot of gravitational potential energy when it's all spread out, and then as we bring the gas cloud into a smaller shape, we have to convert that gravitational potential energy into something else. So we turn it into kinetic energy and heat energy, causing the center of the gas cloud to heat up. And if the gas cloud is big enough, then it has enough kinetic energy when it collapses that the center will eventually start doing nuclear reactions and form a star. You can have gas clouds collapsing that never get hot enough in the center for a star to form, and we'll talk about what happens in that case a little bit later in the semester. So the inner parts of the disk are hotter than the outer parts of the disk. If you think about rocks versus ice, if you had ice particles close to the center of the disk, they would melt or vaporize, so you wouldn't have ice anymore. But rock has a much higher melting or boiling point, and so you can get rocky material closer to the center of the disk than you can ice particles. So the different materials that would have been around during the formation of the solar system, gases, hydrogen and helium are never going to condense, but that's what most of the gas in the universe is hydrogen, and then a bit of helium. So that's 98% of the material available. Then you can have hydrogen compounds in the form of water, methane, and ammonia. Those are going to condense, so they're going to turn from a gas to a liquid at 150 Kelvin. Rocky material, that's going to be solid at much higher temperatures, and then metals like iron, those will be, again, solid at much higher temperatures, but there's a lot less of that. So these are all of the materials that you have to make your solar system, and so that's going to include the sun and then all of the planets. So why do we have terrestrial planets that are closer to the sun and then gas giants that are further from the sun? So there's a term called the frost line, and basically anything inside of that line, any ice that you have is going to be in a liquid form or a gaseous form, so you're not going to be able to form a planetary body out of that material. But beyond the frost line, ices are going to be solid rather than liquid, and so you can form planetesimals out of that material. And the reason for this frost line is that conservation of energy is telling us that the center of the disk is hotter and further from the center of the disk is colder. So this is why we have terrestrial planets close to the sun and gas giants farther from the sun. So you have these rock and metal particles that are close inside of the frost line. So planetesimals are basically the building blocks of planets. So material around during the formation of the solar system, those particles will start to collide with each other, and eventually some of them will have a large enough gravitational pull that they'll collect a bunch of material and form a planet out of all of that material. And so this accretion process is not necessarily a nice, smooth process. It can be very violent. So you have to go from the picture on the left with all of these kind of small planetesimals. Eventually they'll collide with each other and build up into larger and larger planetesimals until eventually they've kind of cleaned up all of the debris in their orbit, and they're now a planet that is spherically shaped and in a nice stable orbit with nothing else that it's going to hit, really. So you start off with a lot of small objects that build up into larger objects. Outside of the frost line, you're going to have ices that can be the building blocks rather than having rock and metals. And also, these planets are far enough away from the sun that there's a lot of gas that they're able to use to build themselves out of, basically. So if you have enough gravitational pull, you can start bringing in the hydrogen and helium gas around you rather than it going towards the sun. And you can think of the formation of a planetesimal similar to, it's like a microcosm of a solar system forming. So there's going to be a disk around the planetesimal that has a lot of material. That material can get drawn in towards the center, and any larger particles outside of it might form into moons, or they might collide with the object in the center to further increase the mass of the planet. And so this is why those gas giants have so many moons and why they still have ring systems. Those are the leftover material from their formation. However, you're in a race against the clock when you're forming your planet. So as soon as the sun is hot enough that it starts doing nuclear reactions, it's going to start putting energy out into the solar system, and that energy will create a solar wind that'll blow any leftover gas out of the area around the sun. So any material that wasn't gravitationally bound to a planet, whether in its atmosphere or in a gas giant, is going to be blown away, and you can't build your planets out of it anymore. So asteroids and comets are basically the planetesimals that were never big enough to pull in all of the material around them and become spherically shaped and clear their orbits. But they also haven't hit anything yet to be absorbed by that planet. So the asteroid belt is made out of rocky material because it's inside of the frost line, and the Kuiper belt and the Oort cloud are made out of icy material because they're outside of the frost line. So if we are thinking of the time where the sun is now turned on, it's doing its nuclear reactions, it's blown all of the gas that's left over out of the solar system, but there still might be planetesimals hanging around that can hit the planets that have formed. So the late stages of the formation of the solar system are a time when some very large collisions can still happen. So one of the hypotheses for the origin of all of the water on the Earth is icy planetesimals, whether those are comets or even bigger, are hitting the surface of the Earth after it's formed and depositing all of their water on the surface. There are some odd moons in the solar system. So Phobos and Deimos are the moons of Mars, but they're tiny compared to all of the other moons in the solar system. So we think these are just asteroids that were captured by Mars, and so this is more evidence that there are planetesimals kind of in the time frame after the solar system formed, that in this case Mars captured them, but you could imagine something this big also just hitting the surface of a planet. And we think that's exactly what happened to the Earth. So we think that a planetesimal about the size of Mars actually impacted on the Earth. So that's going to liquefy basically most of the planet, so it'll be a molten ball. But the energy of that impact is going to spew material out of the center of the planet, and that material is going to start orbiting the Earth. That material will eventually cool down and harden, and we think that's where the moon came from. So the moon is the result of a large impact between the Earth and another planetesimal, and the material that got spewed out during that collision formed the moon. So there's lots of evidence for this that we'll talk about when we talk about the moon later in the class. But the one that makes the most sense to me is if you look at the materials that the moon is made out of, it's all rather light material. So exactly the kind of material that would be kicked out during this collision. So the moon doesn't have a big iron core like the Earth does or like the other terrestrial planets do. These giant impacts also might explain some of the weird axial tilts and rotations that we see. So if something really big hit the planet Uranus, if it was rotating on its axis more or less up and down, and then something really big hit it, you could imagine it basically knocking the planet over and causing it to rotate at a 90-degree angle almost. The same thing goes for Venus. So Venus is rotating in the opposite direction of all the other planets. If you have something really big hit Venus such that it basically causes it to spin the other direction. So we have to invoke these collisions of planetesimals to kind of complete our nebular theory. So this is a picture from the textbook. It's kind of hard to read it here, but it's in the lecture slide, so you can see it there. But basically just shows all the stages of solar system formation. So you start from a giant cloud of gas. That cloud of gas will start to condense into a disk. The inside of the disk will be hotter, so you'll get rocky material. The outside of the disk will be colder, you'll get icy material. And then once things start to form, you'll have big collisions and build up into larger and larger masses. And what you're left with are, for the most part, planets orbiting and rotating all in the same direction. And you'll have some leftover material in the asteroid belt, the Kuiper belt, and the Oort cloud. So which of these is not explained by the nebular theory? Yeah, so we have to add the collisions of planetesimals in order to explain the formation of Earth's moon and the axial tilt of Uranus. So the features of the solar system that point towards the nebular theory are the motions of their orbits and rotations, the fact that we have rocky planets close to the sun and gas planets further away, the leftovers of solar system formation in the form of asteroids and comets, and then we have to invoke the collision of planetesimals to explain the exceptions of the rotation of Uranus, the Earth's large moon, the rotation of Venus, etc.